All right, everyone get ready because today we are going deep into embodied AI.
Oh, yeah.
Really diving in deep. We're going to be looking at this EmbodiedBench paper.
Uh-huh.
This is a new benchmark, right, that's designed to test these multimodal large language models,
Yeah.
MLLMs, as embodied agents.
It is.
So before we get into all the really nitty-gritty details, what I think it's always we should start with like the 1-minute summary for all of our listeners out there. We're like, hey, just give me the quick and dirty. What's this all about?
Yeah, sounds good. So EmbodiedBench is essentially a comprehensive testing ground for embodied agents, and it really goes beyond just simply measuring like task success. It actually dissects like how well these MLMs perform on very specific capabilities like common sense reasoning, spatial awareness, handling, complex multi-step instructions, and all within, visually rich simulated environments.
Gotcha.
And, some of the really interesting takeaways from the research is that current models are surprisingly good at like these high-level tasks, like understanding complex commands, but they really struggle with the finer details of low-level actions and long-term planning, which are obviously, very crucial areas for future research.
Awesome. Super concise. I think that was a great summary. Now, for those of you who stuck around for the full deep dive, let's get into why a benchmark like this is even necessary in the first place.
Well, the field of embodied AI is absolutely booming right now. New, MLLM-based agents are kind of popping up left and right, each with like their own unique architectures and training methods.
Yeah, it's almost like a Cambrian explosion of embodied AI.
Exactly. And with so much innovation going on, it becomes kind of increasingly difficult to compare, apples to apples, so to speak.
Apples and oranges.
That's where EmbodiedBench comes in, right? It gives us this, standardized way to assess and compare these different approaches to make sure we're all, speaking the same language.
Right. It's not just about did the AI succeed or fail, but really like how did it succeed and where did it fall short?
Exactly. EmbodiedBench breaks down performance into what they call 6 capability-oriented subsets.
Okay.
Each one's designed to probe a different aspect of embodied intelligence.
Let's break those down for our listeners. What are we talking about here?
So you have kind of like your base capability, which is just like, does it understand the environment and can it follow basic instructions, right?
Okay.
Then you have common sense reasoning, which is like, can it make logical inferences about the world?
So like, I guess kind of like basic knowledge that as humans we take for granted.
Yeah.
You know that you need to open a door to walk through it.
Exactly. And then there's handling complex instructions.
Okay.
Which, as the name suggests, can it parse multi-step commands.
Gotcha.
You have special awareness, which is like understanding its position in the environment. Can it navigate effectively?
So like, can it walk around the kitchen without bumping into the refrigerator?
Yeah, precisely. Visual appearance understanding, so that's all about like recognizing objects based on their visual characteristics. And then lastly, long horizon planning, so that's like how well can it plan and execute sequences of actions over like a long period of time.
Okay, so not just like go pick up the apple, but go to a different room, pick up the apple and come back or something like that.
Exactly. And, this kind of granular breakdown allows us to really pinpoint where these models are good and where they're bad.
Okay.
And that provides us with like valuable insights
Amazing.
For future research.
Now, you mentioned earlier that EmbodiedBench leverages all these different simulated environments.
Yeah.
What are these environments and why were they chosen?
So EmbodiedBench incorporates 4 distinct environments. You have AI2 Theor, Habitat 2.0.
Yeah, those both sound familiar. I think those are very popular in AI research, right?
Exactly. So AI2 Theor is like photorealistic indoor environments, primarily household settings.
Okay.
And then Habitat 2.0 is much more flexible. It supports a wider range of environments.
Right.
You can have indoor and outdoor scenes.
So AI2 Thor is like the training ground, and Habitat 2.0 is going out into the real world.
That's a great way to put it. And then you have Alfred, which is focused on these multi-step tasks in simulated kitchens.
So AI Master Chef.
You could say that. So they're doing things like following recipes, preparing meals, and completing complex tasks that require, a deep understanding of the environment and reasoning about sequences of actions.
So that sounds like a good test of these long horizon actions that we were talking about.
Exactly.
Yeah.
And then lastly, you have EB manipulation.
Okay, so we've got our AI chef. What about EB manipulation? What is that one all about?
So this one's all about the fine motor skills, right? So, how do you precisely manipulate objects?
Okay.
It tests the agent's ability to control robotic arms and grippers.
So like how dexterous are the robot hands? Can it do stuff like thread a needle or build a tower of blocks?
Exactly. And this, the challenges here really highlight that distinction between high-level and low-level actions that we're talking about.
Right, because understanding build a tower is very different than like the actual like minute movements required to do that.
Exactly. And that's where EmbodiedBench, kind of shines. It allows us to see not only which models can, plan, but also can they actually do it?
Yeah, the what versus the how.
Exactly. And that's kind of where those capability subsets come in, right?
Yeah.
It's like, okay, you can evaluate the performance across all these different dimensions and really pinpoint where the model might be strong in high-level planning, but then weak in low-level execution.
Okay, so we've got our testing ground set up, these 4 different simulated environments. What did the research actually show? Were there any surprises?
Well, one of the things that immediately kind of stood out to me was this really interesting paradox.
Right.
Current MLLMs, they're great at understanding these complex instructions. They get the what, but they really struggle to translate that understanding into like priceless, physical execution.
So they can come up with a gourmet meal, but maybe they can't crack an egg.
That's a perfect analogy. And so we see this playing out, in the result across these different tasks. So for example, in EB-Alfred, models like Claude 3.5 Sonnet performed really well, right? Showing a really sophisticated ability to understand these recipes, plan the sequence of actions, and even reason about like the state of the environment.
So it's like they're a master chef in the kitchen.
It really seems that way. But then you switch over to EB manipulation, where, precise control and dexterity is really important. Even the most advanced models kind of hit a wall, right? And suddenly, that seamless ability to plan and execute these tasks breaks down when you're faced with, these intricate challenges of actually manipulating objects in a very precise way.
So they have the mind of a master chef, but the hands of like a toddler.
Exactly. And this really emphasizes the need for more research into, bridging this gap between high-level understanding and low-level control. We need to figure out, how to develop these models that can not only, grasp these abstract concepts, but then also, translate that into very specific motor commands to interact with the physical world effectively.
Now, you mentioned Claude 3.5 Sonnet. Were there any other kind of standout models in the research?
Yeah, the performance landscape was really interesting. There was, a mix of, proprietary and open source models kind of being put through their paces.
Okay.
And each model kind of exhibited its own strengths and weaknesses.
So it wasn't just like bigger model equals better performance.
Not at all. And, while like the larger proprietary models like GPT-4o and Gemini, they kind of generally achieved like higher scores overall. Some of the open source models, like the Intern VL2 family, showed like pretty strong performance, especially in tasks that require like a deep understanding of visual information and spatial relationships.
So that's really encouraging to see. That means the gap between the proprietary and open source models might be narrowing, which would be great for accessibility and research.
Absolutely. It means more people can, contribute to this field.
Now, beyond just like overall performance trends, were there any other kind of intriguing or unexpected findings that emerged from the research?
Oh, yeah. One of the things I think that's so fascinating about EmbodiedBench is, its very granular approach to evaluating performance across these different capability-oriented subsets.
Right, so it's not just one number, it's multidimensional.
Exactly. And this kind of fine-grained analysis revealed some really interesting patterns. For example, the long horizon tasks consistently proved to be like the most challenging across like all the models and environments, and even those models that excelled at, understanding these complex instructions. And planning, shorter sequences of actions really struggled when it came to, planning over longer time horizons.
So they can go to the fridge, but they can't plan out their grocery list.
That's a great way to put it. And, this finding really underscores, kind of the challenge of this long horizon planning problem in AI. It seems like, current models might be hitting like a fundamental limitation in their ability to really, reason about the future and maintain, a very coherent plan over, extended periods of time.
Now, you mentioned earlier that EmbodiedBench doesn't just look at like the overall success or failure. It actually digs into how these models are processing information, particularly like the visual input. What did the ablation studies reveal about this?
yes, the ablation studies. So they were super revealing. They kind of shed light on how these models are interpreting and utilizing visual information.
Okay.
And kind of busted some myths along the way.
Oh, okay, tell me more.
Well, so you might assume that giving these models like higher resolution images would always lead to better performance, right?
Yeah, of course. More information, better understanding.
Right. But what they found was that that's not always the case.
Really?
In some cases, higher resolution actually led to a decrease in performance.
Why is that?
Well, it seems that, when you bombard the model with too much visual detail, it can be counterproductive, right? It's like information overload.
Right.
They just can't sift through all the data and focus on what's important.
So it's not just the quantity of the information, but also the quality of the information.
Exactly. And we saw a similar thing with detection boxes. So detection boxes, are those like outlines around objects that are often used to, help these AI models, figure out what they're looking at.
Right, like a little cheat sheet.
Exactly. And while those were beneficial in certain tasks, like in EB manipulation where you need that precise object recognition, it actually hurt performance in EB navigation.
Interesting. Why?
Well, it turns out that in navigation tasks, those boxes actually obscure like really important spatial cues that you need to actually plan a path.
Oh, so it's almost like they're focusing too much on one specific thing and they're not getting that broader spatial awareness.
Exactly. And it kind of creates like a tunnel vision, right?
Yeah.
And this really highlights, that we need to be very mindful of how we're presenting this information to the models, right? Because what we think is a helpful aid can actually be creating unintended obstacles.
Right. We need to make sure that the way we're helping is actually helpful and not hurting.
Exactly. And then, speaking of unexpected findings, right, another ablation study, they looked at whether giving the AI access to like multiple images from like past steps, like giving it a little bit of memory, would improve performance. So instead of a snapshot, it gets a little video.
Yeah, I would think that would be helpful for context.
Right. But actually, that backfired.
Oh, really?
Giving them those past images actually made them more confused than it helped.
Interesting. Why is that?
Well, it seems that, current MLLMs, they really struggle to take those snapshots and stitch them together into a coherent understanding of what happened.
So they've got all the pieces of the puzzle but can't put it together.
Exactly. And this highlights another area, for a potential improvement, developing models that can reason about temporal information, cause and effect, and use past experiences, to inform their current decision-making.
So what we would think of as memory, they haven't quite grasped yet.
Exactly.
Now, all of these findings, all the performance trends, all the capability breakdowns, all the insights from the ablation studies, it really paints a fascinating picture of where embodied AI is today.
Yeah.
But what about the errors that these models are making? What can we learn from those?
Yes, the errors.
Yeah.
They say we learn more from our mistakes than our successes.
That's true.
And that's definitely true in the world of AI. So, the researchers, they did a really detailed error analysis, specifically focusing on, GPT-4o, which was one of the top performing models. And they found that these errors could be broadly categorized into kind of like three main types.
Okay.
Perception errors, reasoning errors, and planning errors. And they found that these errors could be broadly categorized into kind of like three main types: perception errors, reasoning errors, and planning errors.
Okay, so perception errors, reasoning errors, planning errors. What do those look like? What are examples of those?
So perception error might be something like, the AI misinterpreting the visual input.
Okay.
So it might mistake a coffee cup for a vase, or it might, misjudge the distance to a doorway.
So it's like its senses are a little bit off. It's not getting accurate information about the environment.
Exactly. And that obviously can have like cascading effects, right?
Yeah.
Because if its perception is flawed, then its subsequent actions are also going to be off.
Right. If you're working with bad information to begin with, can't really get to a good conclusion.
Exactly.
What about reasoning errors? What do those look like?
So reasoning errors are really interesting because they point to flaws in the AI's like logical processing.
Okay.
So it might like correctly perceive, where an object is, but then make a completely nonsensical decision about how to interact with it.
So it's like they understand the individual pieces, but they can't figure out how to put those pieces together.
Yeah, exactly. So, for example, it might try to place an object on a shelf that's clearly too high to reach.
Yeah.
Or it might, try to open a door by pushing on the hinges instead of the handle, things like that.
Okay, so we've got perception errors where the AI is misinterpreting the sensory input. We've got reasoning errors where its logic is just kind of going astray.
Oh, yeah.
And then we've got the planning errors, which I think you said were the most common, right?
That's right. So, planning errors involve the AI essentially generating plans that are either incomplete, invalid, or they just, don't achieve the intended goal. And these were especially common in tasks that required like multiple steps or, these long sequences of actions.
So they can handle the short game, but the long game is a bit of a problem.
Exactly. A good example might be like the AI forgetting a crucial step in a multi-step task.
Yeah.
Like it might forget to, open a drawer before trying to retrieve an object from inside the drawer.
Right. Just little things that as humans we take for granted.
Exactly. Or it might, generate a plan that's technically valid,
Yeah.
but it's super inefficient. So it might like take a really long roundabout path
Okay.
to reach a nearby destination.
So it's like a GPS that gives you technically correct directions, but it sends you like all around town.
Yeah, that's a perfect analogy. And these kinds of errors really highlight the need for, models that can not only generate these valid action sequences, but also, optimize those sequences for, efficiency and robustness.
Right. It's not just about finding a solution, it's about finding a good solution. Now, within those planning errors, were there any other kind of patterns or insights that emerged?
Yeah, so one of the things that they found was this, recurring issue of what they called missing steps.
Okay.
Where the AI would essentially, omit these crucial actions from its plan.
Okay.
So it's like forgetting to preheat the oven before baking a cake, right? A very obvious step, but if you miss it, it can completely derail the whole process.
Right. It's those seemingly small things that can make a big difference.
Exactly. And this suggests that, we need to really think carefully about how we're training these models, right? Are we giving them enough examples of these seemingly, mundane but essential actions? Are we, explicitly rewarding them for generating plans that include those steps?
Yeah, make sure they're not just learning the main course, they're learning all the sides and the little things that go along with it.
Precisely. And then another common planning error that they saw, particularly in those, low-level manipulation tasks, were what they called inaccurate actions. So that's where, the AI generates these actions that are technically valid, but they're not precise enough to actually achieve the outcome.
So it's like having a robot arm that can get to the right general area, but it can't quite grasp the object with the right amount of force.
Exactly. So it might, knock over a delicate object because its grip is too strong, or it might fail to pick up an object because its grip is too weak.
Right, so those fine motor skills that as humans kind of take for granted that seem to be really tripping these models up.
Exactly. And this really underscores, the need for, better low-level control mechanisms.
Yeah.
We need models that can not only plan the general sequence of movements, but also fine-tune those movements in real time.
Yeah.
Adjust their grip strength, the trajectory and the speed based on the specific object and the task.
So moving beyond just the rigid pre-programmed motions to something more adaptable and more context-aware.
Exactly. And then, another interesting category of errors, although they were less common overall, were what they called reflection errors.
Okay.
And these involve the AI, essentially failing to recognize and learn from its mistakes.
So it's it keeps making the same mistake over and over again. It doesn't learn.
Exactly. And, this really gets to the heart of, what we consider true intelligence, right?
Right.
It's that ability to reflect on your actions, identify your shortcomings, and then, adapt your strategies accordingly.
So it needs to be able to understand when it's failing and try something new the next time.
Exactly. And, the fact that these reflection errors were present kind of suggests that current MLLMs, might be lacking in this crucial area, right? They're not good at identifying their mistakes, and they're definitely not good at learning from them and adjusting their behavior.
So they need to be able to understand their own limitations and be able to recognize when they're making a mistake.
Exactly. And this points to a really exciting direction for future research, right? Developing these models that are not only capable of learning from data, but also capable of learning from their own experiences,
So learning from data is one thing, but learning from their own actions.
Exactly.
It's almost like a level of self-awareness that these models need.
Precisely.
To be able to truly be what we think of as intelligent.
And this brings us back to the big picture, right? The whole point of this embodied AI research is to create AI that can not only, understand the world, but also act effectively within it.
Right, taking action based on its understanding and then learning from its mistakes and improving.
Exactly. And benchmarks like EmbodiedBench, they're giving us the tools and the insights we need to make this vision a reality.
So this benchmark has given us a roadmap to figure out how to get AI to that point.
Absolutely.
By highlighting what's working and what's not working.
By providing, this standardized testing ground, a common language for evaluating progress, and then, a really detailed analysis of, both successes and failures.
It allows us to have this common ground to be able to compare the different research efforts going on.
Exactly. And while the road ahead is definitely, going to be challenging, the potential rewards are huge.
Yeah.
I mean, imagine a world where AI can seamlessly collaborate with humans, assisting us in tasks that are, too dangerous or repetitive or just simply beyond, our physical capabilities.
Yeah, it's almost like AI could be like an extension of ourselves.
Exactly.
Helping us to do things that we're not capable of or that are dangerous.
Or just, things that we don't want to do.
Exactly.
Right. Nobody wants to, fold laundry.
Yeah, like if a robot can fold my laundry, I'm all for it.
Exactly.
Well, this has been a fantastic deep dive into the world of EmbodiedBench and embodied AI. Thank you so much for joining us and for all your insights.
It was my pleasure.
And to all of our listeners out there, as always, keep exploring, keep pushing the boundaries, and we'll catch you in the next deep dive.